we started dependency parsing in the last class. Before midsem, we had done constituency parsing and a bit of dependency parsing. We would like to go into important details about dependency parsing. Let us remember that in constituency parsing, we begin to extract the constituents of sentences. So for example, a sentence consists of two large constituents, noun phrase and verb phrase, if the sentence is in declarative form. And then we recursively develop NPs, VPs, because they may themselves consist of more constituents. Okay, so NP, for example, can have a determiner and adjective phrase followed by another noun phrase. Okay, the blue car with a large bonnet. The blue car with a large bonnet. So with a large bonnet is a preposition phrase, and the blue car, the blue is an adjective phrase. The tiny blue car with a bonnet, for example. So we can have quite an amount of complexity below each of these phrases. Dependency parsing, on the other hand, is main verb centric. So the classification problem that we solve by a neural network or by rule-based system or by support vector machine, any classifier, the first problem that we solve in dependency parsing is the main verb, identifying the main verb. So we poll each and every position and ask, is this the main verb? Yes or no. Is this the main verb? Yes or no. So then finally we hit the main verb, and the whole dependency parsing starts from there. So we'll in tonight's class we'll show the dependency parsing algorithm, and we'll see how this classifier is in operation. There is a classifier problem inherent in the constituency parsing also. So that classifier problem is at every position. By position, remember, we mean by position, we mean the position between two words. So the classification decision we have to answer for constituency parsing is this the start of a new phrase? Does this position begin a new phrase? And then after getting an answer yes, we ask, does this position end the phrase? Okay, so all the time there is a decision being taken and a classification decision. And this is what brings NLP and machine learning close to each other. So both parsing frameworks have classification decision. Now we have already learned that classification decisions are tackled by classifiers, and classifiers, if they are not rule based, they are trained from data. So the Penn constituency tree bank is the data for creating constituency parse, and the Prague dependency tree bank is the data for creating dependency parse. So both these data sets got created through many years of effort with lot of expertise, linguistic expertise from a large team of people. And then the labels had to be fixed. We'll very soon see the labels. There are in constituency parsing, there are labels like NP, VP, PP, and so on. In dependency parsing also there are labels. So this sentence we have seen many times. I saw the boy with a telescope. This is the first parse tree. And by looking at the tree, you can immediately say that the telescope is with the boy. Dependency parsing also corresponds to the same meaning. And in dependency parsing, the meaning becomes much more clear. That's why we say that the dependency parser is closer to the deep meaning of any sentence. So here the fact that the boy has the telescope is very easily seen. There is a modifier relation from boy to with. With is a preposition which takes an object. The object is telescope, and telescope is a telescope. Okay, it is a determiner. So the boy with a telescope, shows that this telescope is with the boy. In the other parse tree, the telescope is the instrument of seeing, so it is with me. And that is also very apparent in the dependency parsing. So you can see that the dependency parsing makes the meaning much more explicit than the constituency parsing. So here, the fact that I have the telescope is apparent from the graph itself. Saw is modified by a preposition with. With takes an object, telescope, a telescope. So you can see here the linkage of telescope is with saw, and therefore I have the telescope. So this point, let me make it once more, more clearly. The dependency parsing brings out the relationships between the entities in a sentence much more clearly. And it is the entities and the relationships which contribute to the meaning of the sentence. That's why dependency parsing is closer to meaning extraction. In fact, entity relationship extraction, information extraction, all of them depend in the first step on dependency parsing. So dependency parsing can be considered a very fundamental process and tool in NLP. Now, there are several advantages of dependency parsing over constituency parsing. The related entities are closer in dependency parsing than in constituency parsing in terms of path length. You have seen already how telescope is directly linking with boy or saw through the preposition. So that relationship was not so obvious in the constituency parsing. And the free word order creates challenges for constituency parsing because constituency is reliant, depends on constituency. That is the adjacency of words to form a constituent. So if that does not hold, then constituency parsing runs into difficulty. If the if two parts of a constituent are far apart, then constituency parsing will help. And additional rules may have to be introduced, and that will overgeneralize, for which we have given an example here. I saw the boy with a telescope has this constituency parsing rule. S goes to NP-VP, VP goes to VBD and PPP. VBD is saw, NP is the boy, PP is with a telescope. Now, the verb phrase is now consisting of adjacent words. The boy with a telescope. That is saw the boy with a telescope, which is the complete verb phrase with all words consecutively placed. But you can also have a non-canonical form. With a telescope, I saw the boy, where you want to give emphasis to telescope. With a telescope. With what did I see the boy? With a telescope. So here S goes to NP-VP is fine. But now, S goes to PP and PVP, that is a question mark. So with a telescope is PP, I saw, I is NP, saw a boy is VP. So now this becomes a structure and it can give rise to wrong constituents. Okay, think about this problem that this rule S goes to PP and PVP and the basic rule S goes to NPVP. These two together, can generate ungrammatical sentences, which is often the case if you want to accommodate more language phenomena. Then the previous language phenomena plus new language phenomena, the rules for that can give rise to wrong structure detection. So this is exactly like the precision recall dilemma. You introduce new rules to increase the recall. That means I want to capture more language phenomena, but that can give rise to the fall of precision. So I'd like you to think about whether this rule, S goes to PP and PVP, can give rise to ungrammatical constructs. Okay. So this discussion we had, Ram ne Sham ko dekha, Sham ko Ram ne dekha. Now we have a break in the constituency. Sham ko dekha is the verb phrase, but between Sham ko and dekha, Ram ne has come. That breaks the adjacency of the constituent. So This is a sentence from Jurafsky and Martin. Towards the end of the last class, we discussed this. I prefer the morning flight through Denver. Uh, Here, the dependency parsing is much more succinct and much more compact. So I have hit the main verb here, prefer. For prefer, the agent is I. And what do I prefer? Flight. What kind of flight? The flight, morning flight, and Denver flight. And Denver flight means that the flight is through Denver. So this is a very, very compact representation of the meaning. On the other hand, look at the constituency parse tree. S goes to NP, NP goes to pronoun, pronoun goes to I, VP goes to verb and NP, verb is prefer. Then there is a full NP, noun phrase. The morning flight through Denver. That noun phrase has noun phrase has determiner and nom. Nom means a nominal. Nominal means a noun, essentially. So nominal goes to nominal and preposition phrase. And this nominal again goes to a nominal and a noun. Nominal goes to noun. Morning flight. So because morning flight has to be dealt with special instrument. That's why these norms are introduced one after the other. And these are recursive rules. Norm goes to norm PP, norm goes to norm noun, norm goes to noun and flight. So morning flight, here morning is a noun, though functioning like an adjective. And through Denver is a preposition phrase. So that comes here. So this parse tree is much bigger than the parse tree of the dependency tree. So in dependency tree, how many nodes do we have? We have 1, 2, 3, 4, 5, 6, 7. That is exactly equal to the number of words in the sentence. A dependency parse is created by linking words, whereas in constituency parsing, the tree is created by finding constituents and then linking them. So here you see the number of nodes is much more. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So there are 23 nodes in this tree, whereas here you have just 8 nodes. No, you have 3 and 3, 7 nodes in the dependency tree. So it is much more compact. Now, what is interesting though is that dependency parse tree is often created through the medium of constituency parse tree. So constituency parse tree identifies constituents, and we have already learned the rule that under a constituent, one child is the head, all others are modified. So once the head and modifier are identified, then linking them with dependency parse tree relations is much easier. So constituency parse tree actually makes the job of creating dependency parse tree easier. But of course, dependency parse tree creation has its own independent algorithm, which we'll very soon see. So phrases are like suitcases that put all related things at one place. The morning flight through Denver. You look at this whole subtree here. The morning flight through through Denver. This is under an NP here. So this is like a box which is keeping all other constituents and nodes inside it. Okay, so these are the relative merits and demerits of dependency parsing and constituency parsing. Of course, this reference that is given, Zulawski and Martin, has a very good discussion on dependency parsing. So you are encouraged to look at it. Now, when the dependency tree is created, that is only half the story. We get the tree and link all the nodes with arcs. This is fine. So we are saying that there is a dependency between prefer and I, prefer and flight, flight and the flight and morning, and so on. So there is a dependency. But what kind of dependency? So, for example, there is a dependency between prefer and I and prefer and flight. Are they same kind of dependency? No. I is the agent, flight is the object. So these dependencies now have to be labeled so that the exact nature of the relationship becomes clear. So there is this universal dependency project from 2016. It was an ambitious project. We were participant of a similar project in 1996 that is called universal networking language. So this is Universal Dependency Project. It is of course inspired by many such similar efforts which took place before 2016, where people wanted to give a repository of labels for capturing relationships between words. Now, this effort is very similar to creating the part-of-speech tag labels, for example, which you have already worked on in the form of the assignment. We are also working on support vector machine-based named entity identification. Of course, the assignment is only a binary classification, yes or no, but named entities also have many different types, like person name, organization name, and so many times they are combination. Indira Gandhi Open University. If I take this name of a name of an organization, Indira Gandhi Open University. Here, Indira Gandhi is the name of a person. So the name of the organization contains the name of a person. So this kind of phenomenon, language phenomenon, is also quite frequent. Organizations can have names of persons, then a place can have the name of a person. Swami Vivekananda Road, for example. There, it is the name of a facility, a road. Within that, there is the name of a person. So this is quite common. And there we have to find out the type of the named entity. So person, location, person, place, organization are the very the frequently occurring predominant named entity categories, and they have their subtypes. For example, within organization, you can have sports organization or economic organization, financial organization, and so on. Under facility, you can have road, you can have lake. Okay, um, let's say then the name of a lake could be the Swami Dayananda Lake, for example. So here we have the name of a lake, which is a facility, and within that there is the name of a person. So anyway, now we have the labels, which I remarked last time at the end of the class that all these labels require deep insight into linguistics and machine learning. So these labels cannot be very fine-grained. Then the classification accuracy will be low. They cannot be coarse-grained. Then the downstream application using dependency parsing will suffer. The story is same for part-of-speech tagging. Part-of-speech tags cannot be very fine-grained or cannot be very coarse-grained. Extremely coarse-grained part-of-speech tagging will create problems for subsequent stage, namely parsing. Constituency parsing requires part-of-speech tags. So if part-of-speech tags are, is there a question? Uh, can everybody mute yourself, please? Uh, so if the part-of-speech tags are very coarse, then then constituency parsing will not be helped by part-of-speech tags. Okay. On the other hand, part-of-speech tags being very fine-grained, there are part-of-speech tag repositories which contain 200, 300 part-of-speech tags. They're extremely fine-grained. So their accuracy is typically very low. As the number of classes increases, it is also more and more complex to get high accuracy. So you have to strike a balance. There is a sweet middle spot. And that middle spot requires insight into linguistics and insight into machine learning. So all these labels which have been arrived at, some of them are following a convention. After all, you need a subject in the sentence. So n sub is a nominal subject. Why n, one might consider, and why nominal? Can there be non-nominal subjects also? There can be. For example, running is a good exercise. In case of running is a good exercise, one can argue that running is not really a noun. It is an activity of running. So it can possibly be called a non-nominal subject, a verbal subject. But n sub is a very common label which designates a subject. Let us also remember that subject does not always mean agent. Agent has the capability and the power of thinking to cause an action. There's a difference between agent and subject. Subject is syntactic, agent is semantic. So we already saw an example. John broke the window. John is agent as well as subject. The window broke. Here window is subject but not an agent. Window did not cause the breaking of the window. That would be strange. The stone broke the window. Again, stone is subject but not the agent. Delhi saw a big riot. Yeah, Delhi is subject but not an agent. 1947 saw the independence of India. 1947 is a subject but not an agent. It's a time. So this way we distinguish between syntactic subject and semantic subject. Semantic subject is also called agent. So N sub is a very common dependency relation. And dependency parser often do not have the power of going into further details of whether something is actually an agent or not. So that is given to the next stage of processing. DOBJ is direct object. I prefer the morning flight. Flight is the direct object. IOBJ is the indirect object. And CComp, XComp, etc. So all these relations are there. Let us take a look at some of their examples. N sub DOBJ, IOBJ. Ram gave a book to Sham. Here the main verb is gave, and N sub is Ram. Nominal subject is Ram. DOBJ direct object is book. IOBJ indirect object is Sham, who is the beneficiary. CComp and XComp. I said that he should go. I told him to go. Both have the same meaning. I said that he should go. I told him to go. Both have the same meaning, but the syntactic phenomena are different. I told him to go. Here, go is in its elementary fundamental form. It is called the infinite form or non-finite form. Non-finite form means it doesn't undergo any transformation. It doesn't undergo any morphological transformation. I told him to going is not possible. I told him to went, not possible. But I said that he should be going is fine. So here the main verb can undergo transformations, morphological transformation. In the other case, it cannot undergo morphological transformation. When it cannot undergo morphological transformation, it's called non-finite or infinite. And the other form is called the finite verb. Now, CCOM links the main verb. Notice here that in this sentence, there are two verbs. I said that he should go. I told him to go. Both have two verbs. The CComp and XComp relations always link the main verb with the clausal verb, with the subordinate verb. So I said is the main verb. He should go is within a clause, and it is the main verb of a clause. So it is called a clausal verb. So said and go are linked by CComp. I told him to go. Told and go are linked by XComp relation. So XComp is for non-finite. CComp is for finite. Why this distinction is required? Why did the people who created dependency labels, why did they think that two different relations will be needed? So that's an intricate linguistic phenomena understanding task. Okay, and this also facilitates higher accuracy dependency parsing. It also facilitates subsequent operations like deep semantic labels, question answering, information extraction, sentiment analysis. Those things will be helped if these dependency relations are first of all recognized and placed in the repository level, and then a computational mechanism is created to identify them from the sentence. So, it is a nice thought exercise. Okay, thought exercise to think, what if XComp and CComp were not distinguished? Okay, if we did not have two relations, then what would go wrong? Okay, think about this as an exercise, that why do we need CComp and XComp both? It is just like asking, why do we need so many part of speech tags under noun? So we have NN as the common noun. We have NNP as the proper noun. What if we had only one noun? Okay, what would be the problem? So this is there's a similar kind of question. So as an NLP researcher, whenever an NLP researcher encounters a label, a repository of labels, a sequence of labels, should always think why these labels have been created. Are they complete? Are they correct? Are they necessary and sufficient? That is the more important question. Are they necessary and sufficient? And for necessary and sufficient, you will have to make a two-pronged attack on the question. One side from linguistics, the other side from machine learning. The situation is not different from speech processing or computer vision. In computer vision, we have to make again a two-pronged attack using image processing and digital signal processing, computational geometry. All these ideas have to come, plus machine learning when we do any kind of image captioning and image labeling. Okay, so images also have to be labeled, right? So for example, we may have a scenario and there we have to label a road. So we take the label road and place it there. Take the label house and place it there. We may again combine house and building, maybe combined together. Okay, and we just give one label. So this is the way labels are introduced, and they play a very important role in data-driven AI. So CCOM links the main verb with the finite verb. XCOM links the main verb with the non-finite verb. More dependency relations, all of them are very important. NMOD. NMOD is a nominal modifier. AMOD is an adjective modifier. NumMod is a numerical modifier. AppPos is an appositional modifier. Let's look at all the examples. NMOD, the bungalow of the director. Here, director and bungalow are linked with the NMOD relation, nominal modifier. So bungalow of the director and bungalow are linked. Director is a noun. Bungalow is also a noun. So bungalow of the director. Here director is modifying the bungalow. Not any or every bungalow. It is director's bungalow. AMOD is the adjective modifier, the large bungalow. So we have an arrow from bungalow to large, head to modifier. So large here is the adjective modifier. NumMod is a numerical modifier, 3 cups. And then apposition, COVID-19, the pandemic. There is a relation between COVID-19 and pandemic. Apposition means something that comes as an additional piece of information. COVID-19 is said, and then we are saying it is a pandemic. So that is the additional information. Similarly, Modi, the prime minister. So the relation between Modi and the prime minister is appositional. Okay, it is additional information. So now a question that might arise is that what will we lose if we drop NumMod? If we just say 3 is also an adjective. If what will happen if we drop NMod, cricket bat? Okay, we just say everything as modifier. You can do that, but you will lose lots of fine details which are needed in the subsequent processing. Okay, in question answering, for example. Okay, so whose bungalow is it? If we have only one modifier, then it will require a little more processing to know that it is the director's bungalow. So director's large bungalow. Okay, director's large bungalow. Here we have two modifiers. One is director, the other is large. So if both of them are modifier, then a mindless machine, that means a non-intelligent machine, can think that the bungalow of the large. Okay, the bungalow belongs to large, whatever that large means. So those kind of confusion can arise. And modifier anyway is a very, very big umbrella. Under that you have many different kinds of modifier. Determiner, case, which is preposition, postposition, and other case marker. Conj is conjunct and CC is coordinating conjunct. Let's see their examples. The bungalow, we have an arrow from bungalow to determiner, and the label on that arrow is DET, determiner. Case, the bungalow of director. Remember that the dependency parsing tries to examine for every pair of words if it is possible to have a relationship between them. That's why there is an algorithm, maximum spanning tree based algorithm, which first of all creates a tree or a graph of relations of every pair of the sentence or the phrase. Here, the bungalow of the director. Here we'll assume, first of all, assume that there is dependency between every pair. The and bungalow, there is a dependency. Bungalow and of, there is dependency. Of and director, there is. The and director, there is a dependency. Bungalow and director, there is a dependency. So we have a completely constructed graph, complete graph, where every pair of words is linked. Then we apply a maximum spanning tree algorithm, which is based on a particular weighting scheme. And once that algorithm stops, it isolates only those arcs which are actual dependencies. But we'll look at another algorithm for dependency tree construction that is called transition-based dependency parsing. Conj is, here is an example of Conj. He is sincere and honest. So between sincere and honest, we have a dependency relation, and on that, the relation will be Conj. CC, he is sincere and honest, and is a particle here. So between honest and there is the CC relationship. So the CC relation involves the word and conj is between the two words which are linked by and. Okay, are both needed? Let's look at an example and see. Here is a sentence: the agile athlete runs fast and jumps high. The agile athlete runs fast and jumps high. In this case, we are seeing a dependency parse tree. So let's pay some attention to this parse tree. First of all, root is pointing to runs, saying thereby that runs is the main verb of the sentence. Now, who runs? Athlete. So there is this n subj from runs to athlete. What kind of athlete? The agile athlete. So agile is the adjective modifier and det is the determiner. So the agile athlete forms one constituent. It is very easy to create a constituency parse tree from dependency parse tree. The agile athlete will form one particular constituent. Then runs to athlete, there is n subject. Runs to fast is adverb modifier. Then runs to jump is conjunction. The athlete runs and jumps. And from jumps to and is CC, and jumps to high is adverb modifier. So this particular relation, this particular arc, which has CC on it, jumps to and, that seems like superfluous. We linked runs and jumps with conj. Why do we need another dependency parse relation between jumps and? So this is there for completeness, because in dependency parsing, no word is dropped. Okay, no word is dropped. But there are, of course, two kinds of dependency parse tree. If you run Stanford dependency parser, then it produces a complete and exhaustive dependency tree without dropping any word. And it also produces a compact dependency tree where some words which have been already, whose semantics has already been captured in relationship are dropped. So I have made a note here, linking and is redundant. DP has to show all words. Semantic role labeling, that is a deeper representation than DP, and would drop it. So when we go to a deeper semantic representation, we'll be dropping and. So I hope this is a good representation of the concept that we are learning, namely dependency tree. We'll come to how a dependency tree is algorithmically constructed. If you recall, the very successful algorithm for producing constituency tree is our CYK algorithm, okay, which looks at every pair of adjacent word, and tries to see if a constituency can be created. A constituent can be created. CYK algorithm is that. Here also, we will see a transition-based dependency parsing algorithm. This is what will be created after that algorithm is run. Just a mark how we have placed all the words side by side and then drawn arcs to capture the dependency. And they are labeled also on the dependency. So let me just make sure at this point that I'm audible and all the slides are visible. Can somebody verify?
Yes, sir, you're audible. Yes, sir.
Okay, fine. So let's proceed just one more time, because this captures the dependency tree construction. It's a good example of a dependency tree. So the agile athlete runs fast and jumps high. The main verb is first hit, runs. Who runs? Athlete. How does he run? Fast. Adverb modifier. N subj, because it is answering who runs. What kind of athlete? The agile athlete. Agile is the adjective modifier, a mod. The athlete, a particular athlete, DAT, determiner. Runs fast, adverb modifier you have given. Runs and jumps. So runs, conjunction, jumps. Jumps, coordinating conjunct and jumps to high is adverb modifier. There are two adverb modifiers in the sentence. Runs fast, adverb modifier, and jumps high, adverb modifier. So for some notes for the dependency tree, one, there is a single designated root node that has no incoming arcs. Okay, the root node doesn't have any arcs. So here is the root. You see on this there is no arc, but there is an outgoing arc. With the exception of the root node, each vertex has exactly one incoming arc. So that's why it is a tree. Okay, so every node has exactly one incoming arc except for the root node. So that means this is first of all a directed acyclic graph, and every node has a single parent except root node. So this we know is the definition of a tree. That's why we have dependency tree, not dependency graph, but dependency tree. There is a unique path from the root node to each vertex in V. So root has this privilege. From root, every node is accessible. So let us check. If I take this particular tree, then I start from root here. Can I go to jumps? Yes. I take this solid vertical arrow. From here, by following the conj arc, I go to jumps. And from jumps, I can go to and. From jumps, I can go to high. So from root, I can go to and jumps high. From root, I can go to runs, and from runs, I can go to fast. From root, I can go to runs, to athlete, to agile. So root is that privileged node, which has a path to every node in the tree. That means it has a path from itself to every word in the sentence. So that's that's an important property. So let's absorb this very important property of dependency tree. First of all, there is a single designated root node. Every vertex has exactly one parent. And there is a unique path, okay? No two paths, unique path. This is a consequence of two unique path from the root node to each vertex in B. Having said that, we come to a very important concept called projectivity. And that is required for the dependency tree creation algorithm. The simplest dependency tree creation algorithm makes an assumption of projectivity on the input sentence. So let's understand the notion of projectivity. Again, a fundamental concept. Let's look at the definitions carefully and slowly. An arc from a head to a modifier, is said to be projective if there is a path from the head to every word that lies between the head and the modifier in the sentence. So it takes a little time to absorb this definition. There is a much more graphic description of the definition of projectivity. So first of all, what is projective? Arc, first of all, is the projective. An arc is said to be projective. What is projective? An arc. What is an arc? Arc is a linkage, directed arrow going from head to modifier. Head to modifier. Then what is this particular clause? If there is a path from the head to every word that lies between the head and the modifier in the sentence. So that is the characteristic of dependency tree. It is not adjacency based. The head and the modifier can be separated from each other by other words in a sentence. Okay, we'll see several examples. A dependency tree is then said to be projective if all the arcs that make it up are projective. So first of all, what is projective? Projective is an arc, but then it is extended to say that a dependency tree is projective. And it appeals to the definition of a projective arc. A dependency tree is called projective if all its arcs are projective. And what is the meaning of arc being projective? If there is a path from the head to every word that lies between the head and the modifier. The intuitive definition of projectivity is the following. The dependency graph, that is the tree can be drawn on a plane without crossing of arcs. That is another pictorial depiction of the meaning of projectivity. The dependency graph can be drawn on a plane paper without crossing of arcs. Condition is that all arcs must be on one side of the sentence, either upper or lower, but not both. So let's understand this. All arcs are on one side. Yes, please.
Hello.
Yes. Yeah, tell me. Am I not audible?
You're audible, sir.
Somebody was asking a question. Has he placed anything on the chat box? If your sound system has a problem, you can write the question on the chat box. Okay, maybe he or she will write the question or comment. So these two definitions are equivalent. All arcs are on one side, above or below the sentence, and there is no crossing of arcs. Is equivalent to this definition, which is more formal. Every head modifier pair in the sentence, there is a path from the said head to every word in between the head and the modifier. So you see, there is a path from the head and its own modifier positively. That path has a length of 1. There is only one arc from the head to the modifier. But within the sentence, the head and modifier need not be adjacent. There can be intervening words between the head word and the modifier word. Now the projectivity requires that there is a path from the head to the every word in between the head and the modifier. Of course, the path has to pass through the modifier itself. So let's look at an example. This example is from Jurafsky and Martin, 2019. The JetBlue cancelled our flight which was late. Now let's see. JetBlue cancelled our flight. Now, cancel is a head. Root is, of course, the head of everything. So root to cancel the main verb, I have an arc. Has the person placed the question or comment on the chat box? Yes, sir, Manishit, can you tell me?
No, sir.
No. Okay. So between cancel and JetBlue, there is no intervening word. So the path from modifier, from head to modifier exists there, and there is no other word in between. Okay. Cancelled our flight. Now cancelled and flight again has head modifier relation. Cancelled is the head, flight is the modifier. What was cancelled? Flight. Here is the situation of intervening word. You see the head word and the modifier word are not adjacent. There is another word between them, which is our. Cancelled our flight. It could have been cancelled the flight also. So between head and modifier, we have another word. Now let's see if there is a path from the head to every word which is between the head and the modifier. Yes. So cancel to flight, first arc of the path, then flight to our, the second arc of the path. So from head to our, I have a path. Now flight which was late. So from flight to was, there is the relation called ACL. ACL means it's a clausal modifier of the noun. So flight, which was late. Okay. So from flight, we have the ACL relation going to was. From was, there is a WP. WP is relative pronoun relation here. So all these labels and their arcs, you'll be able to sort of competent with them once you look at the universal dependency grammar and the meaning of each and every relation. It's a useful exercise for you to take any sentence and consult the repository and uh, think of the relation that will exist between the words. And you can verify the correctness of your parsing by running the sentence on Stanford parser, or even you can ask ChatGPT, which is also very competent, to draw the dependency parse tree for you, and you can match your answer with ChatGPT's answer. In most cases, the ChatGPT's answer is correct. So which was late? Was late, it's an adverbial modifier. So it is between the verb of the clause, which was late, and the late, the word late. This is the adverbial modifier, adv modifier. And then let us see if there is a path between intervening words. Yes, flight to was, there is an arc. So flight is head, was is the modifier. Between them there is which. So there is a path. Flight to was to which. Now you might be thinking, isn't it obvious? It will happen for every sentence. Not really. You can write this sentence in a different way. JetBlue cancelled our flight, which was late. Uh, we can write it this way. JetBlue cancelled our flight this morning, which was late. Now I have introduced an adjunct, an additional piece of information this morning between flight and which was late. So which was late is the clausal modifier for flight. I introduced this prepositional phrase this morning here. Now the projectivity is broken. What is our condition? We have to draw all the dependency arcs on one half of the paper on which the sentence is, either on the upper half or on the lower half. When we do so, we find that the arcs are crossed. Okay. And there is no path between the head and the modifier from the head to any word that is in between to all in between the head and the modifier. Let's see. Head is flight, was is modifier. Between them, we have the words this morning and which. So is there a path from flight to was? It is. Path from flight to which? It is there. Is there a path from flight to morning? This morning is between flight and was. There is no path. There is no path here. So flight to was to which, and then it stops. What about this? No, there is no path. So we see that projectivity is broken here. It is broken because of what? Because of the arrival of this morning between flight and which was late. So a key principle for maintaining projectivity is to always try to keep the modifier and what it modifies adjacent to each other. This is also good English, okay, or good command on the language. So this sentence is not very good because head and modifier are not adjacent to each other. So I can change the sentence in this way. JetBlue, okay, this sentence first. This morning, JetBlue cancelled our flight, which was late. Now there is maintenance of projectivity. There is no crossing of arcs. You see, so cancel our flight. Every word is linked from the head. Flight, which was late. So flight to was, and was to which path is there, and there is no crossing of arc, and so on. There is another construction. JetBlue cancelled our flight, which was late this morning. Now this morning has gone to the end. So again, there is a very long arc from cancelled to morning. OBL. OBL is a relationship which is between the main verb and the and an adjunct. Okay, so OBL definition is coming later. Now, the OBL relation is used for a nominal dependent, noun, pronoun, noun phrase of a verb or main predicate. This concerns different cases of prepositional groups, and more generally, it corresponds to an adverbial attaching to a verb, adjective, or other verb. Okay, so this is not really direct object. It is an additional piece of information which is linked with the main verb. All right. So cancelled this morning, it has this OBL relation. Now let's forget the nature of the relation. Let us see if it satisfies the path requirement. Between cancelled and morning, there are these words: our flight, which was late, this, all this. So between cancelled and this, there is a path. Cancelled to morning, morning to this. Between cancel and late, is there a path? Yes. Cancel to flight, flight to was to late. Okay. Then between, is there a path between cancel and which? Yes. Cancel to flight, flight to was to which. Okay. So that condition is satisfied, and it is also all the arcs are appearing on one side of the sentence. So here we have introduced this morning, but we have not disturbed the adjacency between head and the clausal modifier. Okay, that's why the projectivity is maintained. Now, projectivity, as we discussed this, projectivity is not specific to a particular language. It is a universal property. All languages have the notion of projectivity because the notion of head is universal. It doesn't depend on a particular language. The notion of modifier also is universal, and therefore projectivity is universal. Okay, when we say a path from the head to every word between the head and the modifier, it is not dependent on any language. It is universal. So here we have another example, which is non-projective. First, let us take the projective form. We want to convey the meaning: the athlete runs fast, and he or she also jumps high. The athlete runs fast, who also jumps high. This is not a good construction. Okay, you can remember this as a tips for good writing. The athlete runs fast who also jumps high. The meaning is clear, but the head and the modifier are not adjacent to each other. A better construction is this. The athlete who also jumps high runs fast. Okay, so here head modifier adjacency is maintained and the construction is projective. Let us see. The athlete who also jumps high runs fast. So head here runs is the head, and from runs I have a long arc going to athlete. And between runs and athlete, there are many words who also jumps high. You can verify for yourself that there is a path from runs to every word, which is between head and the modifier. Runs to athlete, athlete to jumps, jumps to high, or runs to athlete, athlete to jumps, jumps to who, jumps to also, and so on. But in this case, there is no path. Athlete, athlete to jumps. Okay, runs is the main verb. So runs to athlete, runs to fast, it's fine. Then athlete to jumps, there is a clausal arc, ACL. So between the head and the modifier, there are many words, runs fast, who also. So you see there is a crossing of arc here, and there is no path. So athlete to jumps, athlete to fast, there is no path. And there has been a crossing of arc. It has crossed the arc from root to runs. So one might say that if I bring the roots down below and put it inside, then there is no crossing over. Well, that is not the point. The point is that the root can be placed anywhere in this whole vertical column, and then there will be crossing of arc. And if you want to be more rigorous and formal about it, apply the test of path from the head to every intervening word. That is a much more rigorous test. Now, when I say the athlete who also jumps high runs fast, then I see that there is no crossing of arc and the existence of path from head to every word, intervening word, that condition is satisfied. For other languages also this test can be conducted. JBL ने हमारा फ्लाइट को रद्द किया जो लेट था. JBL ने हमारा फ्लाइट को रद्द किया जो लेट था. So this has a main clause and the subordinate clause, and you can look at the dependency tree which is created and discuss the projectivity. JBL ने हमारा फ्लाइट को जो लेट था रद्द किया. This is a projective construct. The other one, JBL ने हमारा फ्लाइट को रद्द किया जो लेट था. This is not a projective construction. So this way we can develop the theory using the projectivity notion. Now, the dependency parsing algorithm, which I'm going to describe in tomorrow's class, is called transition-based parsing. It is actually essentially a shift-reduce form of parser. Transition parsing gives the correct parse tree if projectivity is satisfied. If the projectivity violation happens, then transition tree produces a tree, but that would be a wrong tree. So what should we do? Because many times the corpus has sentences which are not projective. And projectivity is an additional constraint. When we speak in the flow, we may violate projectivity. So for that, we have other algorithms like MST, maximum spanning tree based dependency construction, tree construction, which we'll discuss a little later. So let us stop today. This was an extra class. Tomorrow's class will be there on Monday. And then we have Diwali. So 31st, there is no class. But we'll have 2 extra classes next weekend, Saturday and Sunday, on Teams. And that will be the end of the course. I'll do this transition-based parsing, dependency parsing, and then move to a few large applications of natural language processing. Machine translation we have already seen. Maybe conversational AI, sentiment analysis. These are large applications, which I'll cover next, making use of the concepts that we have learned. Meanwhile, the SVM and named entity recognition, that assignment should give an idea about the named entity and SVM, but I'll also try to cover some named entity recognition.